Pluto is a far-off and strange midget planet, which was once a member of our nearby planet group's planetary family. However, recent surprising declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They suggest that this frigid world is on a potential crash course with Neptune. But how is it that this could work out? What might be the outcomes of such an enormous occasion? Are we seeing an intriguing galactic peculiarity? Or is there something else to this looming vast impact? Join us as we investigate the possibilities of a Pluto-Neptune influence. Pluto, a former planet that was downgraded to a dwarf planet somewhat due to its exceptional orbit, remains a subject of interest and study in the galactic community. According to recent predictions by leading scientists, Pluto's orbit is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm of a potential risky crash between these two planets that could be a tremendous danger to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our planetary group. It requires a stunning 248 years to complete a single orbit, meaning since its discovery in 1930, it hasn't even completed one full revolution. But the interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, veering off significantly from the nearly round orbits of the major planets. What complicates Pluto's orbit even more is its inclination, angled at 17 degrees to the ecliptic plane. The way Pluto follows is much more extreme compared to other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most captivating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually gets closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to grasp its unique trajectory. Unlike the other planets, whose orbits lie mostly near the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amid these complexities is proof of the intricacies of space mechanics. The three-body problem in space is about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how Pluto's path, Neptune's path, and the Sun's gravity all interact in a complex manner. The terms azimuthal libration and latitude libration, along with the Yarkovsky-O'Keefe-Radzievsky-Paddock YORP effect, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is an azimuthal libration. With regard to Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in keeping their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned significantly above their orbital plane, providing an additional layer of protection from potential impacts. Another crucial element in this scenario is the YORP effect. Named after three scientists who studied how things move in space, it explains how three space objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This pulling affects how they move. For Pluto's case, YORP helps us understand why its orbit around the Sun is so peculiar. Although Pluto's path seems erratic, this effect helps keep it moving smoothly over long periods. The YORP effect shows that even if things in space seem wild and random, certain patterns and rules keep everything in order. All of these components help to keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or deviate from its course. This three-body problem aids in understanding how these components change due to the way these space objects pull on one another. Focusing on this helps us learn about Pluto and our solar system, as well as distant galaxies and their stars. Mathematical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is indeed turbulent, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, keeping the chaos under control. Recent computer simulations have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This resonance helps keep Pluto's orbit consistent. Yet Neptune isn't the only one contributing. Jupiter's gravity also plays a significant role in keeping Pluto's orbit stable, and Saturn contributes substantially as well. These tests show that Jupiter's gravity alone is powerful enough to ensure Pluto stays on a stable path for a very long time, even billions of years. So, Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without running into trouble. These peculiarities are fundamental in the context of the universe for maintaining the order and consistency of celestial bodies' movements. Without these mechanisms, our nearby planet group as we know it would be a place of much greater disorder and unpredictability. Bodies like Pluto could potentially crash into others or be ejected from their stable paths, leading to a cascading impact on other celestial bodies. For Pluto, understanding its orbit is crucial, especially with discussions about its potential collision with Neptune in the future. This gives us a clearer picture of the planetary group's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of harmony through the complex interplay of gravitational forces and orbital mechanics. It also demonstrates the importance of continuous observation and study of these peculiarities to grasp our place in the universe better. Exploring the depths of space often leads us to confront the eccentric nature of celestial bodies, and Pluto's orbit is a perfect example of this eccentricism. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is strikingly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Using virtual encounters has been extremely helpful for scientists to understand how Pluto moves in space. These simulations use advanced mathematics to simulate how Pluto and other space objects like Neptune pull on each other. By tweaking small details in the simulations, astronomers can see how even minor changes can make a big difference in where Pluto ends up. In the late 1980s, these simulations showed something very interesting about Pluto's path. Although factors like azimuthal and latitude libration help keep it stable, its orbit can still be wild and erratic if you start with just a tiny difference in where Pluto is or how fast it's moving. Over many years, its path can end up looking quite different. But even with this chaos, Pluto's orbit remains stable for a very long time, like billions of years. This means Pluto's journey around the Sun has a sort of order to it, even though it seems all over the place at first. Predicting cosmic events, especially when it involves turbulent orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While mathematical simulations provide a solid means to understand and predict the future paths of celestial bodies, they also highlight the limitations in our predictive abilities. These models heavily depend on the accuracy of initial conditions and the complexity of the relationships they simulate. Any slight error or oversimplification can lead to vastly different outcomes, making precise predictions a daunting task. Furthermore, the turbulent nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto reminds us that our knowledge about the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So why are major astrophysicists just now raising concerns about a potential crash between Pluto and Neptune? Despite all these intricate forces trying to prevent such an event from happening, Neil deGrasse Tyson, a prominent astrophysicist and key figure in popularizing astronomy, offers a unique perspective on the mysteries of our planetary system, particularly the captivating case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's stance on Pluto's renaming is rooted in the ever-expanding knowledge of our nearby planet group. He sees the renaming not as a downgrade but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He sees the complexities of orbits like Pluto's as an indication of how much there is still to discover in space. The fascination with these mysteries, especially the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our nearby planet group. His work emphasizes that the more we uncover about space, the more questions arise, urging us to explore further and refine our understanding of the universe. Michio Kaku, another renowned physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often unpredictable forces that shape our universe. Kaku is known for his ability to bridge complex scientific concepts with futuristic visions, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's views on Pluto and its orbit underscore the need for continuous observation and advanced modeling to anticipate and understand potential astronomical events. He views the interactions between celestial bodies as a crucial area of study, not just for academic curiosity but for practical implications. The potential crash between Pluto and Neptune, for instance, isn't just a theoretical scenario but a reflection of the dynamic and often turbulent nature of space. Kaku's futurist perspective urges us to consider the broader implications of such events, from their impact on how we perceive the nearby planet group to the potential need for future space interventions. Kaku's perspective highlights the importance of being prepared for the unexpected in space. His work suggests that the more we understand the forces at play, the better equipped we will be to navigate and possibly mitigate the effects of cosmic events. Both Tyson's and Kaku's perspectives converge on the idea that space is a realm of endless discovery and that our current understanding, while vast, is still limited. Their emphasis on the need for continuous exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not only understanding celestial mechanics as they are now but predicting how they could change in the future. The potential crash scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for robust scientific inquiry, cutting-edge technology, and a readiness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space embodied by Pluto's orbit are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a global scientific consensus that for years to come, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance and the various gravitational influences acting on them. Therefore, a direct crash between Pluto and Neptune is highly unlikely. However, the complexities and potential disruptions in orbital dynamics mean that astronomers must continue to monitor and study these celestial bodies to better understand their long-term behaviors and any potential risks they could pose. While the scenario of a Pluto-Neptune collision is largely speculative and considered improbable with our current understanding, it underscores the importance of ongoing research and observation in astronomy. Advances in technology, including more advanced telescopes and computer simulations, will help astronomers refine their models and predictions, ensuring that we keep pace with the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the unpredictable nature of celestial mechanics both underscore the need for continuous exploration and a flexible understanding of our universe. The potential collision scenario, while highlighting the dynamic and complex interactions within our nearby planet group, ultimately reminds us of the vast, still unexplored regions in our understanding of space. Through ongoing research and observation, we strive to unravel these mysteries, ensuring that our knowledge remains up to date with the ever-evolving universe.